I'm Matthias. I'm from Upbound, and we are working mainly with on a project called Crossplane, as you might have heard of. If not, that's also great, because then we'll do a little bit of introduction. And I'm super happy to do the talk today with Tobias from DFDS, and we are basically looking into how to apply some of the things that we've been using for different use case, I say. Some of the use case that at least we've heard feedback so far, other people have not thought about it immediately. You want to introduce yourself?
Yeah, so hi, I'm Tobias. I'm from Denmark. I'm a former employee of DFDS, actually. I recently changed my job to go and work for Bitcoin Swiss. But that's another story. I've been studying digital twins with Matthias for quite a while. We spent a lot of time looking at how we could apply it in DFDS as a logistics company. And now I'm pivoting to seeing how I can make my digital twins use cryptocurrency to pay for services. But in general, it's sort of the same thing. We're trying to map out how Crossplane can provide an abstraction to manage and control our digital twins and expose the different abstractions that we want to build around these digital twins inside a Kubernetes context that makes it easier for us to work with. So I guess we can just get the show running. First off, we have an agenda, so we're going to do a bit of big picture, where you're going to have to listen to me talk a bit about how this thing came to be. Then we're going to talk about some of the use cases that we worked on while I was at DFDS. And then we're going to talk about digital twins in general. And then we're going to talk about how that translates over to Crossplane and show you what you all came for, namely some coding examples of how that actually works inside Crossplane. Because obviously, if it's difficult to do, it's not worthwhile investing in. So the idea here is that we want to make it easy for people to embrace and reason about digital twins and start building them into their solutions. Because at the base layer, they're not really that difficult to build once you start looking at it. But if you just can move on, Matthias, please. First off, the big picture. So where did all of this come from? Well, actually, it harkens back to the Apollo days, where NASA was talking about something they like to call the mirrored systems. And inherently, the mirrored systems were used to salvage the Apollo 13 shuttle in order to get the astronauts safely back down. So what they basically did was they created a full redundant system of the Apollo 13 shuttle, and then they used that as a way to gauge what was actually going on in the real thing. And then through that type of simulation, they were eventually able to bring things to order. And then after that, things just kind of went silent for a long while until Kevin Ashton came along. He was I think it was like a product dude at Procter & Gamble, and he was like coining this thing, Internet of Things, because that was something that he could, reason about and sell. And then from there on out, it started becoming science. So Dr. Michael Greaves in the US started discussing the idea of digital twins as an abstraction or as a theory at the university level. Then NASA started bringing that in as part of their roadmap, and from there on, I think it was HP and some other guys started working around building some actual digital twins. I think primarily the early systems were for the health sector or something like that. And that led to the point where we are now, where digital twins are now all the rage, because they are a key enabler for this thing that we like to call Industry 4.0. If we can't reason about and predict what our devices will do in an integrated IoT system, it's going to be very hard ensuring that they don't fly into each other or run over people or stuff like that. So this is why digital twins has started becoming all the rage, and we're now seeing, governments invest millions and millions of dollars or whatever into having private companies come in and help them build digital twins for their satellite systems or for their mega trucks or whatever it is they need to basically monitor in real time. So at the high level, digital twins are essentially just a digital tether on a physical asset. So when I try to explain digital twins for my son, I'm like, well, a digital twin is just the virtual representation of your basketball. So when he plays NBA, whatever, and he gets, some sort of thing in that game, That's just essentially a digital twin on something that could be real. In NBA it's not, but in the future it probably will. Because I think what people have really been looking at is this both, physical and digital sharing economy. People who've played, online games will know that you can earn up a lot of stuff, but you can't bring it with you. If we can start building, a sort of a convergence between these things, then all of a sudden this digital twin concept gets a lot more value than it has currently, because you can now bring them outside the realm that they're in. They mimic behavioral models in physical systems, meaning that inherently what they exist to do is to try to simulate what will happen. So on my trip up here, it took me 12 hours to get from Copenhagen to Hamburg by train. That was not very fun. I'm sure if somebody had had a digital simulation, they might have been able to predict at least part of what delayed me. And I think that is what people are trying to achieve. I worked for many years at Ørsted as a consultant. They have huge wind power systems and so on that requires a lot of maintenance. This is also an example of how digital twins can help them, because they actually monitor these windmills virtually, and then they do predictive maintenance to try to figure out when they have to go and fix the windmill. Because the problem with that is that it's hot up here. The problem with that is that a windmill, if you get a single grain of sand in the engine of a windmill, that will destroy the entire windmill given enough time. So this is why this behavioral modeling is also important. They also provide digital control planes for physical stuff. Like I also work with a Danish company called Rambøll. They're a lot into drones. They want to do drones for like monitoring traffic and doing structural integrity scanning with X-ray stuff and so on. The problem is that they have all these cool features, but they have nobody who can buy it, because they don't really have a system that allows them to lease out their drones. And that means the only kind of assignments they really get is like government assignments where they need to go out and do some landfill or plot some area or whatnot. Whereas the real, money for them is if they could make it so that anybody could rent one of their drones for an hour, right? Pay as you go using your smartphone or whatever, your phone or whatever you have. And the last part of it is that the digital twins, they basically tether to their physical counterpart from cradle to grave. So there I like to use the concept of the sneakers, right? So my son got me these very nice Nike sneakers for my birthday. And I was never really into the whole sneaker cult, but I know there are people who buy sneakers and keep them around and resell them for thousands of dollars. And I don't really get why people pay that much for shoes, but it's a thing. Right? So in the future, when we're looking at all of these high-quality merchandises, most of them will probably be born with some sort of digital twin that will be like a certificate of ownership or a bearer bond or something for whatever it is you bought, if it's a designer shoe or a car or whatnot, which will allow people to easily trade these things around or even verify authenticity and all these other things that goes into it. So that is sort of the 4 key reasons why digital twins are essential for Industry 4.0 and what they sort of represent. And if you want to look at it in a sort of like a real-world example, the way that this works is that digital twins is not really a thing. It's more like an amalgamate and like many different things put together. So the idea is that we want to leverage the robotics that we have today. So if you look at the Mercedes-Benzes and all these other car manufacturers, today their assembly lines are probably largely based on robotics and people working in harmony. In the old days it was probably largely people and just heavy machinery. And in the future it will probably only be robotics. Right? But robotics provide us with a way for the digital twin to basically manifest itself in the real world. And that allows it to then carry out different types of work. And then if you pair that with cloud computing, the digital twin is not only allowed to physically engage with various areas, but it can also freely move around the internet, right? Everybody in here probably watched Terminator, and what does Terminator do? What does Skynet do? It flees to the internet where nobody can catch it, right? And then it can just freely move around. In the same way, using a cloud, your digital twin will be able to service many different areas. So if you take this into the context of DFDS, the digital twin would be able to both interface with the ship and with the harbor facility and with the container and do various operations based on its permissions and so on. On top of that, it also has to leverage big data because simulation in itself is only so good, but it also needs to be able to learn. And in order to do that, it needs to do a lot of machine learning where it will collect input from its surroundings and then gradually try to build up itself. And I think that is probably the most tricky part about digital twins in general, because if you look at the current offerings, they're pretty straightforward. They're like a proxy that sits on top of a device. You can communicate with it, but it's not really that intelligent. What we want to get to is a point where your digital twin can not only do small, simple operations, but it can actually reason about the outcome and maybe change its behavior over time. If it finds it's more efficient to load the ship in the middle of the night, then maybe it should start doing that instead of trying to do it during the day where everybody's running around, something like that. And then on top of the big data, we also need Wi-Fi, right? Because if we had to bring a big cable to everything that the digital twin had to interface with, or some sort of local area network, that wouldn't really work very well. We need wide area networks for that to happen, and in general, we need Wi-Fi, in particular because ships don't really come with cables installed. And then lastly, we need embedded systems that allows the digital twins to basically communicate with the different devices. So these are the PLCs of the world. This is basically whatever, firmware we can install on a device to make it so that our twin can do more stuff than simply just, ping it to see if it's online. So that is sort of the example of how it works. And obviously we do all of this because what we want to do is we want to take all of that and basically digitize it, which would then make it look like this, because that allows us to then reason about it in a 3D environment. It allows us to basically treat our physical world as a game. We could start, moving things around, and we might have, drones. We already have drones on some of our ships today that service the ships to watch if people fall off the ships. But maybe, in a year or in 10 years or whatever, the drones will be carrying the containers to and from the ship. And then somebody would literally just be able to sit, in a cockpit somewhere and with a joystick and manage everything. So that is the ambition and why, logistics companies in particular are investing so heavily in the whole digital twin space.
So when we were started looking into this, we needed to, dive or get a little bit more concrete of what we actually wanted to achieve. So we had a couple of use cases we went through to look into, and I'll just fly over some of them here. So the first part is like, why would you use digital twins, and why would you use them at DFDS? The first one was in the whole area of the containers, of the trailers, and that was the first one was to reduce empty loads, right? Obviously to reduce CO2 emissions, but the overall increase the overall efficiency. Another really interesting use case I was not so aware of initially was in ensuring the integrity of certain type of special services like cold storage of these containers. Predictive maintenance, as Tobias already alluded to, is obviously one, and just, a generally tracking one. Another use case, coming from the trailers to rather the shipments is, again, the general routing for efficiency. But as Tobias already said, like there's going to be, many of these digital twins or central sensors about there. So this logical management of these IoT devices was another part that we looked into. And simulation, predictive simulation of these things is another one. So we've got containers, we've got the shipments or the trailers and the shipments, but obviously the terminals is also a big part. There's a lot of things to automate there, and there's like really interesting projects that are going on, and the overall automation of these processes is a big thing. The space utilization at these terminals is another one. As always, increasing the productivity of the personnel at these locations is, obviously another one. And as again, energy consumption for not only the shipment and the containers, but other areas within the terminal is a big topic, as you might guess. So something that we haven't looked into yet, but is really something that I would love to spend more time on. It is also like the interoperability here. So we're not only talking about like a single vendor about like DFDS looking into their containers, but also the interoperability, right? And if we're going into the implementation in a second, you can start seeing some of this is where you can agree on a common standard and interoperable with other companies, like in this case Volvo, around moving these digital twins around. All right, so let's talk a little bit about what a digital twin actually is, and then we'll look on how we would getting these things going with Kubernetes and Crossplane.
Mm-hmm. Cool. So a digital twin, like I said before, is just a tether on the real world. And that means that in a sense, the digital twin becomes the proxy between our IoT devices and our various UIs or different applications we want to use to interface with the digital world. And that means that often the digital twin is sort of I guess you could call it a transient microservice that lives at the edge. And it allows various TCP IP connections from devices, and then it typically talks with the IoT devices using something like MQTT or events or something like that. Sometimes it'll do straight up calls if it can, sometimes it'll just send an event. But that means that essentially what this is all about is trying to model this proxy, and this is no different from what we did in the good old days when we had to do remoting for messenger applications, right? When remoting object needed to have a proxy and call a remote system because the network wasn't really reliable, and the edge, it's somewhat the same situation. But essentially, the IoT sensor has the embedded system that offers the digital tether, so you can think about that as like an interface that the digital twin can mount to take control of the sensor. Then you have essentially the proxy itself, which facilitates the communication between the IoT device and the people wanting to interface with it. Often people are interfacing with many devices at the same time because they'll do one logical command, and that will then turn into many other subcommands that different devices need to behave on, or behave with, like load the ship. Well, that requires the drones to go and get some stuff and other things to open doors and whatnot. And then lastly, the business will then interface with this using, hot displays on their phones or, desktop applications or web applications, depending on what they really need to do. And the way that we tried to reason about this was we tried to say, well, digital twins are sort of broken into three pieces. First, you have the prototype itself. This is kind of like when car manufacturers, they make a clay chassis for a car to try to figure out if it's streamlined when it comes to air resistance and all this stuff. In the same sense, you typically try to build something that provides a basic abstraction that fits with the particular twin that you're trying to model. That allows us to explore the design before we start implementing it, which makes things a bit easier to reason about. Then you have digital twin instances. Digital twin instances are the stuff that's linked to my sneakers. So for each pair of shoes that Nike spits out, they'll birth a new instance of a digital twin. They're only ever associated with one prototype, right? My shoes can't both be a shoe and a car. That's going to be maybe in the future, but right now at least they can't. And they rely heavily on eventually consistency, right? Because that's where we've all arrived at the end of the day now, with systems using events to communicate and becoming eventually consistent. And lastly, they need a shit ton of data, because a digital twin, when it gets born, is akin to an infant. It will only learn about the person using the product over time. It will only learn about the context the product is being applied in over time. And that means that it needs to slowly grow from a state of being able to just be on-off to a state where it can be maybe on-off or exploring or whatever it is it decides to do. Lastly, we have the aggregates, and this is because, like Matthias alluded to, on a ship there's tons of sensors. There's also tons of digital twins, and sometimes we need to reason about the ship as a whole. And this is where we say that the ship doesn't really have a digital twin. The ship is just an aggregation of many different digital twins that is hosted within it. So in a way, the ship becomes a bounding context or some type of container that wraps all the other stuff. And that basically acts as the facade for communicating with everything else, which means that you send your command and control messages to your aggregate, and your aggregate will then take care of spreading that out. Anybody who ever worked with aggregate route patterns and stuff like that will recognize this type of behavior from how they work. Because aggregate routes exist to protect internal data structures. In the same way, digital twin aggregates exist to both protect but also share twins amongst other aggregates and so on. But those are the three key concepts that we deal with when we're trying to model our digital twin systems. And then based on that, Matthias and we did a bit of work, and we tried to see how this would look in a cross-plane context. And again, I think Matthias will show us that now.
And it's interesting, right? Because you start off with these general patterns, like a prototype, an instance, and an aggregate, and you wonder how to map this. And actually, when I was revisiting the slides yesterday, I was actually going through. It's like, oh, maybe there's a different mapping. But let's look into this. So I think the first part, and we're like, this is Kubernetes. Like I'm preaching to the prior. Is like we know the benefits of Kubernetes, right? It's a great platform to be integrated to. We have this declarative model. We have the resource model, the eventual consistency. And with the vendors out here and with being basically everywhere, we know this is like a common platform. And it's not only a common platform, but it's like all different kind of tools are starting to integrate. I had the conversation with Victor back then. It's like, okay, let's look at other tools. How could they all be integrated? And we came, within a minute, we came a tons of lists of things that we should try and see and how they could map to these. So it's from different kind of clients to backup, observability and policies. So these are all things that at the end of the day you need to provide on the platform. Now, are these all super suited well for this use case? Maybe not, but the point is they're there, and you can get started. You stitch these things together, and you have something up and running before you even do a lot of actual coding. So, what do we do with Crossplane here, right? Well, how do we map this to Crossplane? I guess a short primer to Crossplane. Crossplane is a way of describing an external API within a Kubernetes cluster, within a control plane, how we say. And we basically have this abstraction layer on top of it where we can say different resources. The typical examples are always these cloud resources. So you have your database, you have your VPC or something, and you get them up and running in your Kubernetes cluster. And then we have this abstraction layer on top of it that basically the composite resources, the XRs, what we call them, to map them together into a specific API, right? And that's like the usual stuff we do with Crossplane. But you can map this to a digital twin platform. And now we're like jumping straight away into the domain model. So what we here have is a couple of a basic domain model, right? We have a terminal that knows about trucks and ships, and on each truck or ship there is a container. And now the question is like, okay, we've got these, and we're going to instantiate, and we're actually going to see that in a minute. And if you want to jump ahead, you can see the demo there. But basically, what we're going to do is create these digital twins with kubectl. We're basically going to say, give me a new ship. Right? So the question is, what does a ship entail? And that's where cross-plane compositions come into place. So a cross-plane composition basically tells, okay, a ship is, and in this case, a set of IoT sensors, right? A set of sensors that knows something. And they can be different. They can be about, GPS devices or other things. They basically combine these. And this is as I said, when I was thinking about it, looking over the slides, actually, I'm thinking that the whole control plane is the aggregate, but we can discuss that later. But this is like one of the mappings. Like we have an instance, we have a prototype, and aggregate. All right, so let's actually look into what this could actually look like. So you see actually something running. Let's see here. All right, so you can still see my screen? All right. So this is GitHub. I showed that previously. You can look at it. So first of all, let's investigate. So I've did the cleanup, and if you look at the pods installed, there's nothing installed. There's no pods running, and we're not going to install any pods, right? We're talking here about Crossplane, and the whole idea is that we are using Kubernetes to manage other APIs, in this case, IoT sensors. But if you install Crossplane, or in this case, Upbound, which is the same thing, you see, a couple of minor pods, and we can go into these if we want later. But basically, Crossplane gives us a couple of, CRDs that we can work with. And the compositions might be one of them, configurations, and different things. But what you already see is that we have like different vessels here, right? And you can allude to the URL here is that it says GPS. So we can actually look like what providers do we have, what kind of GPS or IoT providers we have, and there is like a dummy provider and a GPS provider. All right. So let's install the platform itself. So what this basically does is like, okay, let's use the existing providers and let's install a couple of abstractions that describe my IoT systems. So what we can now see is that we have 4 different types, right? We have a container, we have a ship, we have a terminal, and we have trucks. And we can also look at how they're implemented. These are all dummy, obviously, for the demo. And you can look into these, and everyone familiar with Kubernetes obviously sees these, typical resource definitions, but they're now a digital twin in our systems. All right. So what we're next going to do is we're going to initiate some of these instances, right? We're going to create a terminal. We're going to a couple of trucks, and to make it a little bit more interesting, I'm actually going to look at the systems, right? So, no, I don't want to print anything. All right, now I forgot the shortcut. All right, I got to do it this way. Wait. Oh, this was the shortcut. All right, I got it. All right, so far we're looking at the upper hand. You see, like, okay, we're tracking all the terminals and ships in the system. Currently, the system doesn't track anyone, but now we're going to install a couple of examples, right? And what you see at the top hand, you can see the terminals, right? And they're currently not ready. The system reconciles the ready state, and below it's looking for a couple of ships, and it's looking for different latitudes, longitudes where they belong. And you see which terminals they belong to, right? So we've got, obviously, we've got like, what do we have, 6 ships here, 4 are underways, and 2 are in the terminals. And the terminals are now already also all have all their census data. And you can, like, these are 2 examples, right? But you can kind of like see where this is going. So I think we're almost at time, but one thing I did want to show is that obviously, you can use the standard Kubernetes means to work with these, right? So you can, only look for all the terminals that are in Denmark. You can do some, like, custom reporting. It's like, okay, where are the trucks? And show me only the terminals. All these things. And again, you will be look into the demo on the links to see all of them. And lastly, there's obviously some interaction patterns. A very simple one is that if you look at all the ships here, and you look at the Humber Viking, it's currently in Copenhagen. So, you can obviously think about that this is actually going to be rerouted to Valencia, and look at this. Now, this is an imperative way of doing this. You would actually install some policy that would update it. But I hope you see where this could be going. All right, Tobias, you need to speed up.
Cool.
You
So I guess the conclusion that we got out of our research and the work we did at DFDS was that digital twins have a lot of challenges still to overcome in order to become truly viable in mainstream business. I think in general they benefit a lot from Kubernetes because it basically provides a cloud-native operating system, I guess you could say, for the twins to run on. And Crossplane provides very generic control plane capabilities that allows me to turn my ship into a literal control plane that allows people to do anything with it that they are allowed to and that they want to do. And digital twins are also ideal for containerization because at the end of the day, it makes it easier for them to move around between infrastructures, right? You could literally use Velero to just back up your container workload in one cluster and move it somewhere else. And finally, I think the next steps that we need to look at is how can we make this even more robust in a cross-plane context? How can we get the Siemens and the other companies of the world to come out and build their own IoT providers so they can tap into the upbound cross-plane ecosystem and start providing ready-to-use abstractions for the companies that are trying to, somehow put their business on a trajectory with Industry 4.0 and automation and the world of tomorrow that we're all talking about.
Yeah. So I think the part that interests me most, so as for question, is like if you look at Kubernetes and take everything away and you look at this story now, which API would you want to manage with something like a control plane? Which kind of like digital twin scenario, but maybe there's also a very different scenario. And that's something that I would like to learn about. And I guess that's it.
Thank you. Thank you so much. Just a reminder that if you do have any questions, please pop them into the app now. I think we don't have any. Oh, there is one. Amazing. Thank you. Just in time. What is the advantage compared to an application that manages the digital twins?
I think it's primarily the scalability and reusability that you get from having Kubernetes CRDs that can easily be extended and recomposed. I tend to reason about Crossplane as a box full of Duplos, where each Duplo is its own little thing, and I can build new structures from that. So that is the main advantage of this.
Yeah, you caught me when we talked and discussed about it, like some iterative development around these, right? There's like a certain aspect a team can start doing, and then another team is like, okay, now there's a new sensor, new aspect that we want to integrate. So it's a nice integration pattern where different teams can start iterating. It's an extension model built in.
Yeah.
All right.
Cool.
Two more popping up. Amazing. So what was the response from the business to this concept? That was the same question.
I can answer that fairly quickly. Yeah. The business has been talking about digital twins for 5 years until Matthias and I actually sat down and did it on Kubernetes. They hadn't written a single piece of code to do it, right? So the business wants this. If you look at the bigger competitors like DHL, they recently published like a 30-plus page PDF document on digital twins and logistics. So pretty much everybody and their mother who's in logistics is racing to be first in this area.
Okay, and next question. Backstage was mentioned in the talk annotation. How
I
is
can
it
answer
used?
that as well. So I worked with, before I met Matthias and Upbound, I was working with Spotify on Backstage. And we were using Backstage as the software catalog for our things. We were managing a self-service portal for the cloud, and within that, we also wanted to put the digital twins and all these other things. So that was, just using something that was out there that was growing in the ecosystem in general and fairly easy to wire together.
Okay, we have two more. You look like you want to nab one?
Yeah. Well, the first one is perfect. Seems like a good segue.
Sure.
Obviously, if you look at Kubernetes, the primary standard use case was a couple of CRDs, and then the general CRD mechanism came out, and then we had a few more. Now with Crossplane, we have now many more, right? We have not only 10s, 20s, 50s, 100s, we're actually going to 1,000, couple of thousand CRDs. And interestingly, there is some limits in Kubernetes and the API server, but that's part of our, from Upbound, what we're solving. And if you look for it, Nick has just posted a blog post on how we're fixing that in Kubernetes upstream.
Okay, very cool. And last question, is this running on a zero-node cluster? Smiley face.
No. It's all running off EKS cluster and DFDS, and I guess Matthias is running.
I'm running locally kind.
Like
yeah, I'm not relying on the cloud when I'm doing a talk.
All right, thank you so much. We're on time, so perfect. Cool. And
right.
another round of applause, please, for our speakers today.
Who did the questions?